Okay, so let me go back to a question that was asked. And the question is, I did not understand the integration of psi star something equals to infinity and then P1, P2. P1, P2, I don't know what that is. Oh, yeah, okay, I see. Yeah, this thing, okay. So, yeah, so basically what it is that if you go back to the definition of a Hilbert space, the Hilbert space comes with an inner product. So we have to define what this inner product is. And what we are doing here is that we are saying that, in our Hilbert space, in the continuous case, the vectors in our Hilbert space are simply functions, right? Psi1x, psi2x, dot, dot, dot. There are an infinite number of these functions. And why are they? Well, we can go discuss that later. And then what we want to have an inner product, and suppose we want to have an inner product between psi1 and psi2. So this x, this is just a component of this vector psi1, right? So the inner product should be independent of x. So how do we make that inner product independent of x? Of course, we integrate it. And we integrate it over the natural range of x, because x is going to have the interpretation of spatial coordinate. So it should go from minus infinity to plus infinity. And then here we want, so this is the inner product, psi1 of x, psi2 of x. So this is the inner product that we are defining for the Hilbert space, okay? And this just is natural inner product in this case because of the Born interpretation. So now that we have defined an inner product.
So will that 2dx, will there be 2dx?
No, because here it's the same x here and here.
So I meant integration minus infinity to plus infinity dx, and then after that line you.
Oh yeah, sorry, yeah, you're right. Yeah, very good. Thank you. Yeah. So yeah, I didn't sleep last night for various reasons, so that's kind of showing. All right, so okay, and then what we can do is that we can say, what is the norm of a vector? A norm of a vector is the inner product of the vector with itself squared. Well, the norm squared is this thing. So this is going to be minus infinity to plus infinity. And okay, so no, okay, sorry, so then we want to apply this to the momentum eigenvectors, which is psi p and psi p prime. So psi p has the form of as 1 over square root of 2 pi h bar and e to the power minus I p x over h bar. Now, if I take psi p of x and star with itself, then this, what is this? This has an exponential like this. This this guy has an exponential like this, and this guy has the complex conjugate. So those things are phases, so they cancel out. So this is nothing but 2 pi h bar. So now if I take this guy and do the integration from minus infinity to plus infinity, I get infinity here, right? So this is, a divergent integral. But if I take psi p star of x and psi p prime of x such that p is not equals to p prime, so, if you just now do the integral, and, this is an integral you all know how to do, is if you do, you get, again, I'm putting this is going to be 0. Right? So this is just a generalization of the fact that if you have two phases, well, basically sine squared and cosine squared, they give you 0, right? Sorry, cosine and sine integrated give you 0. So we can combine these two equations in one equation, and there is like good motivation for this, which is saying that if this is psi p and this is psi p prime of x, then the integral is 0 if they are different, but if they're the same, they're infinite. But it's infinite in a very particular way. In a way such that the right-hand side is a Dirac delta function. Okay. And what is a Dirac delta function? It's basically an infinitely thin and infinitely high spike, but the area under the curve is 1. So if I were to integrate this whole thing over p, d of p, then I would get 1. Okay. So I hope that answers your question, World War III veteran from the future. All right, so
So would you scroll up a bit on the right hand side on the Hermitian adjoint proof?
yeah, this one.
Yes, a bit up. So you took ddx of psi star x. The ddx was operating on
Psi star of x.
psi star of x, but before that it was operating on phi of x. So how does that
Yeah, so
ddx
right. So
move?
this is called integration by parts, and you know it is that if I have d over dx of say psi star, or doesn't matter if it's star, this is d of phi star dx of psi plus phi star.
Oh, I got it.
Yeah,
Sorry, I
it's okay.
didn't
Yeah,
remember.
no, yeah. So this is called integration by parts. Okay, good. Anything else? Okay, there's a question about the pop quiz. Um, sorry, the question asked to find Hermitian matrices, but from the options I could find only one of 3 Hermitian matrices. Okay, right. Let me come back to that. Okay, what because I have to log out of this whole thing. Let me come back to that at the end of this lecture.